Okay, guys. Cool. Okay, we're going to learn about gravitational field today. We're going to learn specifically what gravitational field is, what the formula for gravitational field is. You're going to learn a different version of this formula, which will also look a lot like the formula for electrical field. You're going to get gravitational field at Earth's surface. You'll get gravitational field anywhere within the vicinity of the Earth. And then we'll talk about the fact that the magnitude of gravitational field is always equal to just the acceleration of gravity. So don't let the AP exam fake you out on that issue. If they tell you the gravitational field is in your head, you should always think, oh, that's the acceleration of gravity. And then finally, or not finally, we're going to get the gravitational field at a point between the two planets. And then finally, we'll talk about the or I think before that, I'm going to talk about the gravitational field inside a planet. No, I think after this, I'll talk about the gravitational field inside a planet, and we'll also talk about if you can have a gravitational field of 0 between two planets. So let's get started. Gravitational field. Yay. Woo! I agree. Okay, gravitational field. Okay. Gravitational field is the same idea as electrical field. It's a characteristic of a point in space. You can't have a gravitational field. A gravitational field just exists. You can cause a gravitational field, but you can't contain one. A gravitational field is just a characteristic of a point in space. And what it is the gravitational force per unit mass. Gravitational force per unit mass. It's the same idea as electrical field, which was electrical force per unit charge. So my gravitational field, which is a G with a vector symbol over it. I put the vector symbol over it to show that electrical field has, gravitational field has direction. But the gravitational field is just going to be the gravitational force over the mass. That's simple. Is anyone in their head right now multiplying both sides by m? Because if you multiply both sides by m, and you think of gravitational force as weight, well, what are you getting when you do that? Yeah, weight equals mg. So I just want to tell you again, gravitational field is no different than acceleration of gravity. It's the same darn thing. Let's compare it a little bit to electrical field. I want to remind you, electrical field, in this case, the field lines point away from the charge. Okay, or electrical field, in this case, the electrical field lines point towards the charge. Alrighty. But gravitational field, let's say this is a planet, in which direction are the gravitational field lines going to point? Anyone thinking it towards the planet? Yeah. Will they ever point away from the planet? No, because gravity as a force, gravity is always attractive. Just like every single student in this class.
Oh.
Yeah. So right off the bat, you don't have to ask yourself what direction, you don't have to use your cleverness to figure out what direction the gravitational field lines point. They always point towards the planet. Okay, great. Well, let's go ahead and do a really simple problem, okay? Let's suppose I'm in the vicinity of a planet, okay? And I choose this point right there. And I say, I want to know what the gravitational field at that point is. And so just like we did with electric field the other day, I'm going to just put a mass there and see how much force it feels. And once I put the mass there and I feel the force, I can get the gravitational field. You guys okay with that? So here, I'm going to put a 2 kilogram mass right there, okay, and I'm going to find that that 2 kilogram mass feels 10 newtons of force. Please find for me, what is the gravitational field at that point?
2 grams
Is that Mr. Lawler's room? For musical instruments? Hey, they look really cool. Alrighty. Hey, this is not that hard of a problem. We got 10 newtons over 2 kilograms. How many people are getting 5 newtons per kilogram? Wait, not all of you. Was it too easy? Okay, great. So you guys okay that the gravitational field is 5 newtons per kilogram? Okay? So you tell me, what's the acceleration of gravity at that point going to be? Thank you, Chris. 5 meters per second squared. Yes. Let me see what we got here. Shy eye, get out of jail free. Oh, right now. Okay to drive south. Good for you. You got someone to masquerade as your mom, and now you're driving all by yourself.
No one can do my mom.
Does she sound really Indian?
She kind of, like, whenever she calls different places, she adopts a different accent. I don't know why.
Good for her.
Yeah. Like, if she's really mad with the customer service, she gets, like, stern with, like, an Indian accent. It's funny.
Good for her. My goodness.
Someone sounds black all the time.
Okay. So, you guys okay that the acceleration of gravity is 5 meters per second squared because the gravitational field is 5 newtons per kilogram? Well, why am I able to do this? Tell me, what do you notice about newtons per kilogram and meters per second squared? Yeah, they're the same darn unit, right? Okay, but I just want to let you know, the newton is kilogram meters per second squared over kilograms, right? And so the kilograms cancel, leaving you with meters per second squared. But the AP exam is going to try to fake you out. They're going to talk about the gravitational field is 12 newtons per kilogram, and in your mind just go, oh, the acceleration of gravity is 12 meters per second squared, because they are the same unit. Okay, great. So I just want to make that really clear to you guys. In fact, in my period 2 and 3 classes, I literally wrote it out. Magnitude of gravitational field is always the same as the acceleration of gravity. But maybe with you guys I won't write it out, I'll just say it in symbols. The magnitude of the gravitational field is always equal to the acceleration of gravity. It's never any other way. Okay, great. So we did that thing. Let's go ahead and get the gravitational field a certain distance away from Earth. Okay? Get gravitational field. How far away from Earth do I want to be? How about 2 times 10 to the 7th meters away from center of the Earth? Let's go ahead and do that problem together. Then I'm going to give you another problem to do. Okay? So here's what I've got. Here's planet Earth. Okay? And I want to get the gravitational field at some point away from planet Earth. Well, just like we did with electric field, if I want to get the gravitational field at this point here, I'm going to put a little test mass there. I'll call it m0. And now I'm going to get an equation for the force on that little test mass. Remember, this here is Earth, so that's going to be the mass of the Earth. So let me just go ahead and put gravitational field equals force per mass. The force on this mass is going to be given by Newton's law of universal gravitation. So it'll be G times the mass of the planet times the little test mass over the distance squared over the test mass. This guy's the force. This guy's the mass that the force is being exerted on. And what do you notice happens to the test masses? Yeah, they cancel, just like what happened with the test charges the other day. And so I end up with just Gm over r squared. So just as electric field in the vicinity of a point charge is given by kq over r squared, the gravitational field in the vicinity of a large mass is going to be given by gm over r squared. And if you don't remember this, you can just always go right back to your Newton's law of universal gravitation and you're fine. Okay, so let me tell you the mass of the Earth is equal to 6 times 10 to the 24th kilograms. I'd like everyone to please plug into that formula. Get me the gravitational field 2 times 10 to the 7th meters away from the center of the Earth.
Nope, you must do it in your head.
You crazy.
Nope, you gotta do it in your head.
Oh, do you guys remember what G is?
No.
My bad.
6.67
Oh, 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. Let's see if I get the same answer as you guys. Oh my goodness. Really? Are you guys getting like 1?
Yes.
I just made that up totally in my head. 2 times, that was random. 2 times 10 to the 7th and we got 1. Look at us.
Publish your discovery.
And are you guys okay that the kilograms cancels one of these kilograms and the meter squared cancels the meter squared and I end up with just newtons per kilogram? How many people got 1.0? Yay. Okay, good for you guys. Okay. Any question or problem on this? Then can I ask you another question? I could give you a scenario where you don't have to keep plugging into gm over r squared over and over again. What if I told you I chose another point, a point that was twice as far away? So let's say I had this point in space and I wanted to know the g at that point. I just doubled the distance from the center. So now the distance, instead of being 2 times 10 to the 7th, it's like 4 times 10 to the 7th. Without doing any, of this stuff, what's going to happen to my gravitational field now?
It's going to be a quarter of it.
Chris says it's going to be a quarter of it. Does anyone agree with him? Yeah, good for you. Chris, how'd you know?
Because if you double it, you're going to square it, and it's on the denominator, so it's going to be by a fourth.
Yeah, beautiful. You double the distance, you're going to square it, but it's in the denominator, so it'll be 1/4 as much. Yeah, inversely proportional to the square. Great. So here it'd be 0.25 newtons per kilogram. Great. And of course, if I tripled it, what would I have to divide the 1 by now? 9. Yeah, good. Okay, so I just want you to be aware of it. That's an easy way to do it. All right. Well, hey, it's time to use this formula even more. I want you to get the gravitational field at a point, that was caught on tape. The gravitational field at a point between 2 planets. Let's do this one. And then shoot, man. Then I'll tell you a couple more things and we'll be done. All right. Here we go. The mass of the moon.
The mass mass of the moon.
The mass of the moon is 7.4 times 10 to the 22 kilograms. The distance between the centers of the Earth and moon equals, and I'm really rounding here, 4 times 10 to the 8th meters. You already know what the mass of the Earth is, 6 times 10 to the 24th kilograms. You know what G is. Get me the gravitational field at a point midway between the Earth and the moon. Please do that now. I'll even make a little drawing. All right. Moon. I need the gravitational field right at that point. Good luck. You're getting two separate and distinct gravitational fields. What are you going to do with them after you get them?
Add them.
Add them or subtract them? If you're subtracting, you win.
What? Интересно. Tell me when you guys are done. G times the mass of the Earth over the distance. All right, I declare you guys done. What'd you get for the gravitational field due to the moon? Good, 1.23 times 10 to the negative fourth, or 0.00012, if you don't mind me, doing that thing. So 0.00012 newtons per kilogram. And what'd you guys get for the gravitational field due to the Earth? 0.017.
Yeah, 0.01, approximately. 0.0100. My calculator has 0.0100. I don't know what you guys have. Okay. So tell me, the final answer, what's the final answer to this problem going to be?
1.
Nah. Go ahead, let's just ignore sig figs. Here, just a second. Okay, there we go. So what's the acceleration of gravity going to be? Or the, the gravitational field? Are you guys getting 0.00988? All right. And tell me, in which direction?
Right.
Yeah, towards Earth. Towards Earth. Okay. So you see, even when you're halfway between the moon and the Earth is still exerting a lot more force on you than the moon is. So if you were to just let yourself go, you would slowly accelerate towards the Earth, and then you go faster and faster, then you slam into the Earth. Let me ask you this. Is there a point between the Earth and the moon where there would be no gravitational field whatsoever? Noelle was nodding her head. Noelle, if so, where would it be, approximately?
Well, more towards the moon.
Yeah, why more towards the moon?
Because like where you currently have it at the midpoint, it's still, the gravitational field is still towards Earth. So in order to have zero, you have to go more towards the moon.
Yeah, good for you. Yeah, in fact, we can actually find that out. And I'm going to show that to you. I'm not going to, ordinarily I would make you figure it out on your own, but I'm just going to show you. I need the gravitational field of the Earth, and we'll call this the distance from the Earth. I need the gravitational field due to the Earth to be equal and opposite to the gravitational field due to the moon, right? Which means the G's cancel, and I end up with the ratio of the mass of the Earth to the mass of the moon, equaling the ratio of the distance from the Earth squared to the distance of the moon squared. Which means I can take the square root of both sides of this equation, and I get the square root of the mass of the Earth over the mass of the moon equals the ratio of the distance to the Earth to the distance of the moon. And luckily, God, our Heavenly Father, our Creator, the unmoved mover, He happened to make the mass of the Earth and the mass of the moon have an 81-to-1 ratio. It's just so we could plug into this radical formula and end up with just 9. Right? Because the ratio of the mass of the Earth to the mass of the moon is about 81-to-1. So there it is. So whatever this, this distance is here, if I call this d, then I need this distance to be 9d, and I will be at a point with 0 gravitational field. Now, obviously, it's hard to keep that. If you could get yourself rotating with the moon, then you could always just, you don't even have to do anything. You would just continue. Although that's kind of weird. Could you keep rotating? Here's the Earth, here's the moon, and here I've got gravitational field of 0. Then describe the motion of this point. If the gravitational field, this moon is orbiting the Earth, right? The Earth is orbiting the sun, but if the gravitational field here due to the moon and the Earth is 0, what's an object at this point going to want to do? What's that? Okay, float away. Tell me, what do objects do when they have 0 acceleration? When they have 0 gravitational field? What are the 2 types of motion something that has no acceleration can have?
Velocity.
What's that?
Constant velocity.
Yeah, constant velocity. Either rest or constant straight line motion. So could this guy stay at that point? This guy's orbiting. This guy is going that way, right? So eventually, what's this guy going to end up doing? He's just going to run into the moon. You see, it'd be really hard to stay there. Yeah, that point exists, but in no time at all, that point is gone, and you need to get to the next place where it is. Well, the next place where that point is in a circle, but you don't get to travel in a circle because you don't have any force on you. Only things with centripetal force get to travel in a circle, and you don't get to travel in a circle. Does that make sense to you guys? Okay, so, but there is a scenario where you could have bands of regions where the gravitational field is always 0, or not always 0, but the gravitational field would keep you moving in a circle. And that's a situation where you got lots of moons. Okay? If you got lots of moons, then you start developing these bands where they just stay in orbit. And, like Saturn, And so you've got these bands, they're not G equals 0 because you need some gravity for them to keep going in a circle, but, I don't know why I'm talking about it, but I'm trying to talk about why you get rings, but I think that's not important. Don't worry about rings. Okay. Okay, there's one last thing I need to talk about, and that's the gravitational force inside a planet. Here, last thing. Gravitational field inside a planet. Okay, so here's my planet, and we know if the gravitational field right here is G, okay, and I'm going to designate G to be the gravitational field at the surface of the planet. We know that if I double my distance from the planet, I'm at this point, we know that's going to be 1/4 G, okay? But what if I go here? What if I cut my distance in half? Well, we know if this was charge, if these two charges are some distance d apart, and the force on this charge happens to be F, if I cut the distance in half, right? Then the force ends up being 4F. Is that what's going to happen here? Is this gravitational field here going to be 4 times G? Please think about this for a second. Do you think the gravitational field will be higher here because now you're closer to the center of the planet? Or not? What do you think? Someone tell us. Someone be like Brian Terse. Last period, Brian Terse, it was like the first time he'd ever said anything in class. And he told me why it can't be that way. What do you think? Okay, well, let's just have a vote. How many people say, yeah, the gravitational field here will be 4G? How many people say it's not going to be 4G? It's not acting like this. Okay, good. So why? Why do you think not? What is it about this scenario that makes you think no? Yeah, Earl.
When you're at the outermost area, you have the whole mass of the planet that's like attracting you. But if you're halfway inside, then you have, well, not half the mass, but less mass attracting you in towards the center of the Earth. So, small g.
You guys okay with that? How many people were thinking that but just didn't want to say it? Huh? Okay, good for you, Alejandro. Next time, make sure you say it. Yeah, he's totally right. If I'm at this point, I've got a bunch of the mass of the planet pulling me to the left, but I've got a bunch of the mass of the planet pulling me to the right. So it can't possibly be 4 times, not if I've got a bunch of the mass pulling me in the opposite direction. You see what I mean? In fact, the only way it could be 4F. What would I have to do to this planet? If I wanted to move there, what would I have to do to the planet to make it so that the gravitational force would be 4F? Yes, Noel? Yeah, shrink it, smush it down, you know? And can you tell me, is there something that happens out there in the heavens where it suddenly shrinks down really, really small so that now you can get really close and experience incredibly high gravitational forces? Yes, Alejandro?
Black hole.
Yeah, black hole. Yeah, that's the only way this is going to happen with gravity. So here, it's something different. And shoot, what time is this class over? 37. I don't know if I'm going to be able to tell you everything about it. Maybe I'll tell you that Monday. Yeah, I'll tell you about it Monday. I'm just going to tell you what it becomes. Okay, here's what it becomes. Okay, if A is the fraction of the radius you're at, then the gravitational field becomes A, or the new gravitational field becomes A times the gravitational field at the surface. And I'm going to show you why on Monday, because it's actually interesting. It's called Newton's theory of shells, or Newton's theorem of shells. So I think it's kind of interesting enough to show you. But I just want to tell you right now, if you're here at 1/2 r, then your gravitational field here, I'll call it G prime, is going to be 1/2 times G. Or if I was here at this point, which is, let's say I told you that this was 2/3 r, the distance from there to there is 2/3 the radius, then the gravitational field here ends up being 2/3, and I'll call that G prime, ends up being 2/3 times the gravitational field at the surface. And I'll tell you why on Monday, because we don't have enough time today. So, hey, that's all I got. Oh, can I tell you one more thing? Do you see these 4 problems? The gravitational field sheet on School Loop. You're going to have to go on School Loop to get that, because I didn't make copies and pass it out because I wanted to save a tree. I wanted to save an entire stand, an entire forest of trees by not giving you that one sheet. Okay? All right, so just remember this. Just remember, this. And I think you'll be fine. Bye-bye. Wait, bye-bye.